Okay, good morning, good afternoon, good evening. Welcome to today's Siemens Global webinar. Today's topic will be looking at improving aerodynamics of Eclipse business jet with CFD and design optimization. I'm delighted to welcome as your speakers. Their bios are up on the screen, so I'll just touch on a few points as we have quite a packed morning to get through. We have delighted to welcome Darrell Rittenberg, PhD. He's a Director of Aerospace and Defense for SimCenter Star CCM Plus and the SimCenter portfolio. He has over 20 years helped engineering organizations leverage CFD to drive innovation within their design process. He's a senior member of the AIAA and is a member of the Inlet Nozzles and Propulsion Systems Integration Technical Committee, as well as a member of the CFD 2030 Integration Committee. So very warm welcome to Darrell. Following up from Darrell, we have a customer voice. We're delighted to welcome Jason Borden, who's a senior engineer for aerodynamics and performance at One Aviation. Jason, again, has spent 20 years working with aircraft in areas from flight test to conceptual and preliminary design. He has a focus on improving airplane efficiency to minimize energy needs and operating costs. So very warm welcome to Jason. And following up from Jason, we have Chris Nelson, PhD, who's an application specialist for aerospace here with us at Siemens. In this role, Chris assists the global Siemens support team as they help our aerospace customers succeed in their use of SimCenter Star CCM Plus. He also acts as an advocate for aerospace interests within the program management and development teams, and is also a member of the AIAA and a member of the Vertical Flight Society. Very warm welcome to you, Chris. And finally, we have Aaron Godfrey, who's a technical specialist. Aaron works as a technical specialist concerned with the solving of engineering challenges here within Siemens, and has been with the company for over 5 years and has a Master of Science in Mechanical Engineering from Utah State. So very warm welcome. Those are your speakers today. Without further ado, Darrell, let me go ahead and unmute you. I will pass you over the ball.
All right. Thank you, everyone, for spending a little time with us this morning. We have a really interesting study that we're going to go through, and I'd like to take just a few minutes to kind of set the stage, so to speak, on kind of how does modern engineering practices and what did they take from historical practices that got us to where we are today in aviation. And I like to start with this image because I always find it fascinating. One, because I'm an avid cyclist and looking at this bike and thinking to myself, wow, you know, here's a bike from close to 100 years ago, and it's really not that different than the bike I'm riding today, at least in principle. But what makes this bike really interesting is who built it. And that, of course, was these two gentlemen, Orville and Wilbur Wright. Now, everyone in aviation is probably aware of the famous December flight of the Wright Flyer, where Orville and Wilbur were able to demonstrate the first manned-powered flight, which was a great achievement. What's even more astounding is if you think about their background, these are two gentlemen who really didn't have that background, that engineering background, yet they were able to develop an aircraft over the course of notionally 10 years. I also find it interesting that we think of the fathers of aviation as Orville and Wilbur Wright, but we often miss out on our friend Samuel Pierpont Langley. Langley, of course, was competing with the Wright brothers with his aerodrome, and actually he had flown a few weeks earlier than the Wright brothers. Unfortunately, his man-powered aircraft crashed. And as a result, when we think about the fathers of aviation, often Langley gets overlooked, except for those people perhaps who are more tuned into the industry, which certainly if you're on this call today, you probably are aware, for NASA Langley, for example. But when we think about the Wright Flyer and what engineering processes were used to develop this aircraft, in addition to test, and mind you, there was a lot of testing that went on over the course of 10 years to fly this vehicle, the guys actually set up within their bike shop the world's first wind tunnel. And this was back in the 1890s. They set up a very simple box. This is actually from the Wright Brothers Museum in Dayton, Ohio. And as you can see, it's basically a fan with a balance. And if you look on top of the tunnel itself, you'll see a number of airfoils. These airfoils were actually metal, so they were forged, which means to make changes, they had to get in and try to reshape these airfoils, and then look at the values that they were getting for lift, specifically, using the wind tunnel. Now, of course, there's been a lot of improvements in wind tunnel technology. As fate would have it, I found myself in late 2003 at the NASA Ames wind tunnel, where they were doing a full-scale model of the Wright Flyer in the NASA Ames full-scale wind tunnel to celebrate the 100-year anniversary of that historic flight. But going back to it, to think for a moment that a lot of the measurements that were done, a lot of the design for the aerodynamics, were basically done through a test, fail, redesign, test, fail, redesign strategy, which works very well. I'm going to fast forward a few decades and start to think about the way CFD and other computational methods found their way into aircraft characterization. And what we find is that over the years, we've actually seen the adoption of high-fidelity fluid dynamic calculations, specifically in the area of characterization for things like aero databases. The main objective in this case is to understand across a number of operating conditions what a vehicle in a given configuration is going to perform like. And this can be done as long as it's in an automated way. You can actually run these things in the background, and we've certainly worked with organizations who have run tens of thousands of CFD simulations to help build out those performance databases. The great thing about this is it allows you to evaluate, let's say, areas that are difficult to test, whether it's high speed or very low speed performance. So what does that play into design? So when you think about how CFD is being used, you can extrapolate that into the application of design space exploration. And that's really where we're seeing the most innovative designs coming from, because it allows engineers to perhaps extend their thinking beyond their intuition. This is actually based on some work we did with UTAS on optimizing or improving the performance of thrust reverser cascade array. And the objective here was to see whether or not we could use design space exploration to improve overall performance. And over the course of 160 or so of evaluations, we actually improved the performance of this array quite a bit. Now, we were interested in understanding how this approach could be used to a more complex problem, because from an objective perspective, we really want to get to a point where we can go from, say, CAD design. And the typical process we see today is we will often wait until we have a more final design before we start doing high fidelity simulation. And what that means is you have a relatively long lead time, which doesn't give you a lot of time towards the end of a program to understand how you might improve performance. So conceptually, if we can decrease the amount of time it takes to get to that baseline simulation through automation efforts and through scalable computational resources, we can start to look at hundreds, if not thousands, of designs. And that allows us to get to a better design point much earlier in the design process. And that's really what's driving this discussion here this morning. We'll talk about work we've been doing on improving nacelle performance. So to do that, we need to understand where are those bottlenecks in the simulation pipeline. Through some great work, we've actually got to the point where we understand today that a lot of the time an engineer spends with simulation is in problem setup, post-processing, and pre-processing. So we looked at this as a challenge and developed a pipeline approach that allows us to very quickly go through from CAD to mesh solution and ultimately analysis in a single pipeline. And this can really work to decrease the, say, time investment required by an engineer to look at results. And it's that wall clock time that we care about deeply. But then the question comes, well, if I'm a small organization, well, how do I extend this methodology? Sure, if I'm a company like Boeing and I may have large computational resources at my disposal, If I'm a small company, I may not. And that's where we start to look to the cloud as a really, in this way, it's equalizing the playing field. So when we think about small companies and how can they compete with these large companies, we actually see that leveraging cloud resources with an appropriate licensing model allows organizations that are perhaps not as resource rich to run those same set of thousands of simulations, and to do that in such a way that we actually can be competitive with those organizations that have more resources at their disposal. So cloud resources, AWS being a prime example of that, they actually did help us early on in this study with some resource to do our preliminary characterization. And we've extended this to a number of applications. This is some work that we did a few years back with Martin UAV with the main objective to improve aerodynamic performance of the duct system, to optimize. Basically, you have two competing objectives here. One is for VTOL, where you want to maximize thrust. But once you're in cruise, you really want to minimize drag. And so looking at design space exploration and evaluating thousands of designs, we were able to make some significant improvements to their loiter time just based on an improved duct design. So that's kind of an introduction to how and the main methodologies we use to help organizations really tackle these complex problems. What we're going to do today is actually walk through an example from a business jet and really kind of dive into more of the technical detail. And with that, I'm going to transfer the ball over to Jason, who will take us through some of the learns related to nacelle design.
All right. Thank you, Darrell. Let's go ahead and go to the next slide. Okay. So I worked with the Eclipse 550 jet aircraft, which, for those of you familiar with the aerospace industry, probably know that it's a very light jet, fairly non-traditional from the standpoint of small jets, because it has 6 seats, is aimed at targeting the design space under 6,000 pounds to be able to fit in Part 23. Operate at a decent Mach number, Mach 0.64, 41,000 feet, and use some of the smallest Pratt & Whitney engines that you can get, and really try to target low operating costs for either business jet crowd or owner-operator people. So next slide, please. And we wanted to look at trying to design a new nacelle on the airplane to see if we could get some improvements over the existing design. When you are trying to design an inlet on a nacelle, the general rules of thumb that you get typically from the engine manufacturers have to do with defining the inlet length as a factor of fan diameter. You'll get some criteria that is recommended best practice rule of thumb kind of thing from them for that, and also for the inlet lip cross-section shape being a function of an ellipsoid. Looking on the right, the thing that they're trying to minimize on that is any inlet distortion. These are the kinds of images that you'll see if you look at say a quick Google search of inlet distortion on an engine inlet, and so you're trying to minimize inlet distortion at the fan face while still maintaining good pressure recovery, and that is generally something that happens better with you have to kind of optimize the play between a short inlet and a long inlet to try to find a place where you don't have a whole lot of boundary layer growth, but you don't stress it too much to lose to basically not even their trip to turbulent, because then you get bad pressure losses that way as well. So the rules of thumb that you get from the engine manufacturers generally give you a fairly safe design that gives you good pressure recovery for cruise conditions and acceptable inlet distortion for off-cruise conditions where you're at high angle of attack or high side slip values. Let's go to the next slide, please. When you're looking at the Eclipse jet targeting something that was really as light as we could make it, and those traditional rules of thumb is that it gives you a safe inlet, but it really doesn't necessarily give you a much lighter design, much higher performance design. They're just rules of thumb. They just generally work. You can find other designs that perform better, such as if you do an iterative design, say manually, like what was done originally on the Eclipse. But it's labor intensive. And just a quick note about how using the rules of thumb, you can end up with a much different aircraft. Other jets in the design space that compete with Eclipse on the kind of mission, they're much heavier and they cost much more to acquire and operate because using the rules of thumb just generally results in a heavier design. So next slide. So that was the problem, to see if we could get a better inlet in the nacelle using an automated optimization so it was not quite so labor intensive as what was done originally. We need good analysis fidelity, such as what you get from the Reynolds average Napier-Stokes type of approach with CFD, but it's traditionally been very expensive computationally. You need a lot of resources to do that. Automated setup for doing that and seeing if we could leverage the cloud clusters was certainly something we were very interested in. So once again, the goal was to get better cruise drag and inlet pressure recovery, but still be constrained by having acceptable inlet distortion at the fan face, as what is required from the engine manufacturer guidelines. Next slide. This is going to lead into the CFD setup, and that is going to be covered by Chris. So, Chris, I'll turn it over to you.
Thanks, Jason. Like Jason said, this next section of the presentation is going to go over kind of the first part. If you remember the earlier slide that Darrell showed with the design going from 1 to hundreds, this is the first part of that process where we're going over the baseline simulation and maybe a little bit further. So next slide, please. Picking up where Jason left off, like he said, we were looking to come up with a nacelle design that would minimize the overall drag and then maximize pressure recovery at engine fan faces. Since there's 2 fan faces, that means 2 objectives. Similarly, for the design constraints, the inlet distortion for each engine shouldn't exceed that of the baseline condition, so that 2 engines, 2 conditions. Next slide. Having kind of decided what we wanted to do, we needed to come up with a geometry that we could do it with. And the key is you want to end up with a parameterized CAD file that allows you to automatically generate the various test designs as you vary the parameters in the CAD file. So we obtained a half body of the fuselage minus the nacelle, and this was provided in a static format. Then we were given the nacelle design in a parameterized CAD file, which was great, and then we came up with, using the internal tools within SimCenter Star CCM Plus, we took a design for the nacelle pylon and modified it so that as the CAD parameters are varied and you get the different potential ranges of of nacelle designs, we came up with automated processes so that everything would be stitched together and you wouldn't have a gap between the pylon and the nacelle, or you wouldn't have the pylon punching through into the nozzle, for example. Then when all of that was done, we reflect it so that we have a full vehicle, since we know that we're going to do side slip conditions for some of these runs. Next slide, please. So having got a geometry, we then have to create a mesh or a mesh pipeline. The key here, again, is that everything needs to be able to run automatically. So we can't use some of the very capable tools that SimCenter Star CCM Plus has for surface repair, for example. But we have a very powerful set of tools that don't require manual intervention. And so we used those and came up with a polyhedral mesh that has 48 million cells. We used the new parallel poly mesher that was released first with SimCenter Star CCM Plus version 2020.1. Highly recommended if you haven't tried it already. The mesh does use prism layers. There are 21 cells in the prism layer, and this is, it should be noted, a high Y plus mesh, and accordingly, most of the cells immediately adjacent to the wall have a Y plus value ranging from 30 to 100. And let's go to the next slide. So having got a mesh, now we move on to setting up physics and boundary conditions and so on. We were using RANTS simulations, ideal gas with Sutherland's law for viscosity, second order discretization with a Venkat limiter to prevent spurious oscillations. Turbulence was handled using a Mentor SST model. Boundary conditions were relatively straightforward. We have a characteristics-based far field boundary. We have no-slip walls for the solid walls, and then for the engine inlet and nozzle exhaust, we used mass flow boundaries. All of the operating conditions were then parameterized so that, again, once we get into the design exploration aspect of things, we can have Design Manager go through and manipulate these conditions in a straightforward fashion. And let's go to the next slide. So we ran an initial test. We picked one set of conditions, ran it, made sure it worked. But then really we needed to figure out what are the operating points that we need to look at. Because as I'm sure you know, when you're doing a design of and certification of an aircraft, you have to consider all kinds of different operating conditions to make sure that things are safe. So there were quite a few conditions that are considered in this case for the Eclipse. Of those, 20 are flaps up conditions, and since the main part of our vehicle was a static CAD, we didn't really have the option of setting up flap motion and that sort of thing. So we restricted ourselves to the flaps up conditions, and then we ran an automated design sweep for all 20 conditions for the baseline aircraft. The main objective here was to identify what are the critical operating points for the design optimization that we're going to do. At the same time, we validated the convergence criteria to make sure that what we set up gives robust, reliable answers for all the different conditions. And what we ended up with was setting up a maximum number of iterations, it's 5,000, and then we set up an a running average monitor for both lift and drag coefficients, and an asymptotic convergence criterion based on that running average. Then running through this design sweep, we verified that we got, to the best of what we could tell, reliable, robust solutions, and that gave us some confidence that the mesh pipeline that we had set up was going to work when we got into the larger design optimization study. Next slide. So in terms of the specific conditions that we decided to look at, the first one was easy, design cruise conditions. That's where you live this vehicle is going to live most of its operating life at cruise conditions. So that's absolutely critical. But beyond that, we picked what would be the most extreme cases that we could see. Out of those 20 cases, we found 4 that represent kind of the worst case scenarios for the nacelle design constraints and objectives. So the first one is higher speed but lower than cruise speed, but with a really high side slip and the nose up at cruise altitude. The next 3 are low speed and low altitude. You have one that's extreme nose down, one that's nose a little bit up but very high side slip, and then the last one is a very high angle of attack. So having selected these design points, then the results of that earlier design sweep gave us the baseline values that were then used in the optimization study. Next slide. And Aaron is going to take over now and tell us more about how that all worked out.
Thank you, Chris. Let's go ahead and advance to the next slide, please. Okay, so the first step, once we have our baseline model set up, we're confident of the accuracy, we've done the analysis about the operating conditions, is to create an optimization problem statement. So as Chris kind of outlined, we have 5 operating conditions, and we have 2 objectives. First is we're going to try and minimize drag, and we're also simultaneously going to try and maximize the pressure recovery. And as you mentioned, due to the fact that we have 2 nacelles, that's technically 2 objectives there for each operating condition. The question comes, how do we handle a design problem as significant as this? If we have 5 operating conditions and 3 objectives, that's a total of 15 objectives for the entire study. And some of you may be familiar with optimization techniques, and one approach that you might be aware of is to do like a Pareto optimization, where we allow the optimization algorithm to independently consider all of the objectives and try and characterize the trade-offs in performance between those objectives. That strategy really isn't recommended for more than about 3 objectives, though. It becomes very difficult to converge those studies, and even if you manage to do that, interpreting the results can be very challenging. So an alternative way is to sort of aggregate all of the objectives and constraints into a single performance value that the optimization algorithm can then try and maximize. And anytime you have as many objectives and constraints as we see here, that's almost always going to be the preferred methodology. So you have to come up with a sensible weighting system. The algorithm that we use allows you to really pick any number of total weighting points you like, and then distribute them in whatever way you like across all the objectives, and in this case, across all the operating conditions. So you can see here in this slide, the total weight that we're giving the problem is 12. And the way we distribute that is, well, first of all, we kind of made a comparison between the objectives, drag and pressure recovery, and said, is one of these more important than the other? And it was determined that the drag objective should be given more weight, and we decided that it would have 2 times the weighting of the pressure recovery objectives. I kind of want to emphasize that clearly there's something kind of qualitative going on here. There's no fundamental equation or anything that you can use to spit out, the quote-unquote right weighting. You have to rely a little bit on your experience and your understanding of the problem, and sort of use a little bit of intuition about what it is that really makes a good design when it comes to looking across all the objectives. So we kind of came up with a 2-to-1 weighting for drag versus pressure recovery. Looking at the 5 operating conditions, it was kind of obvious, that crews should be given additional weight because that is the condition at which the aircraft will spend the majority of its operating life. So we decided to give crews equal weighting to the other 4 operating conditions combined. And that's how we kind of end up with a total of 12 points and how we've sort of distributed them. In addition, we applied a constraint, like Chris mentioned, that said the inlet distortion on both nacelles must be less than or equal to that of the baseline values. So in total, we end up with 5 operating conditions, 15 objectives, and 10 constraints for our problem statement that we're going to pass on to the optimization algorithm. Let's go to the next slide. So the next thing that we want to consider is the parameterization. And in this case, the CAD for this aircraft model came to us already in CATIA. And CATIA is a very capable platform for creating parametric models. And so that's what we decided to use, given the CAD was already generated within that platform. There's 8 total CAD parameters that we decided to look at. There's an exhaust angle and an inclination angle that you can see here. It's sort of controlling the orientation of the nacelle to the pylon and the rest of the body of the aircraft. The inlet diameter, inlet face angle, inlet length, the lip depth, the lip width, and then the toe angle. And these animations that we're looking at here are just sort of cycling back and forth between the minimum and the maximum values that were considered for each of these objectives. Go to the next slide. So we have our design space, we have our problem statement, and the question becomes, what kind of strategy do we want to use? And there's a nice analogy that can be made to like mountain climbing, where you have an unknown terrain. It's very similar to design space exploration. For example, you go out, you don't know if you're going to come across icy conditions, if you're going to have to navigate a crevasse, loose gravel, all of these things. Well, the correct tools to navigate these different kinds of obstacles, it's not the same. You need different tools to deal with ice than you do loose gravel. And it's kind of similar within design exploration, where a design space may be highly multimodal with many different local maxima and minima. It could have a lot of discontinuities, could even have very large holes in the design space. And none of those details are known a priori. And therefore, it can be challenging to select an optimization algorithm, many of which have the advantage of performing well in a certain type of design space, but poorly in others. And similarly, if you're mountain climbing and you know that you may come across all these different kind of treacherous conditions, you wouldn't want to bring only the equipment needed for ice. You would certainly try and plan ahead and make sure that you had everything that you need for all the different kinds of conditions that you could come across. Now, the traditional approach to design exploration is where you sort of limit yourself to just a couple of tools, those that are inherent to a specific optimization algorithm. What we've tried to do is sort of re-envision that and ask, well, is there a way to actually bring the advantages of all of these different techniques to a problem simultaneously? And we have a proprietary algorithm called Sherpa. Maybe the best way to think of it is that it's kind of like a library of other well-known academic or canonical algorithms for doing design space exploration. It has your gradient-based techniques, things like nonlinear sequential quadratic programming, simplex methods. We've got simulated annealing. We've got swarm techniques and certainly a heavy emphasis on evolutionary or genetic heuristic style algorithms. And what that means is it's not limited to only having the advantages of one of these algorithms. It actually has access to all of them. And more importantly, it is capable of applying these simultaneously to your design space. That kind of hybrid approach is one of the most powerful aspects of the algorithm. It really allows it to get excellent performance in terms of, the amount of improvement you expect to see for a given number of evaluations in the design space. It's also adaptive, meaning that it has the capacity and access to the underlying tuning parameters of each of these algorithms, and it will modify them in real time as it is learning about your design space. So we felt like, given the complexity of this problem, and especially the computational cost in performing each CFD evaluation for a design, it really needed to have a sophisticated exploration and search strategy like we have with Sherpa. Let's go to the next slide. Okay, so let's start discussing some of the results. Here you can kind of see an animation as we go through and look at, this is each of the designs that was considered by Sherpa as part of the optimization study. We had a total of 8 parameters, and as a general rule of thumb, we like to consider a minimum of 10 times the number of parameters for our total evaluations. Certainly more is always better, but given the expense here, we decided to start at that lower bound. We always have the ability to extend from there if we feel like we need to get the kind of performance that we're interested in. So 80 total evaluations. I will mention that 17 of those resulted in errors of some kind. These are predominantly related to the CAD. Some kind of combination of parameters results in a CAD operation that fails to execute or something like that. But, it's also possible to get errors due to meshing or maybe the solver not converging, and we did have a handful of those as well. We ran 2 simultaneous designs at a time, and each of those was occupying 240 CPUs, total of 30 days of runtime. A significant investment. It should comment that this included the queue time. The high performance computing cluster that was used for this is one that is very busy, so there was a fair amount of queue time. We weren't able to at the end of the study go back and determine the exact wall time across all of the different jobs. Let's go back one more slide here. So you can see here we're looking at the drag history. These are normalized, and they're normalized by the baseline values. So a value of 1 indicates that we have the same performance with drag that the baseline design had. And obviously we're trying to minimize this, so values below 1 are better. And you can see here that in the total number of evaluations that we looked at, we actually found a pretty significant improvement. The blue line is tracking the performance improvements of the drag at our cruise condition. And you understand from our weighting that we described earlier that is really kind of the most significant objective of all of them. It carries the most weight. And you can see here that the algorithm managed to find a very substantial improvement. If we look at the drag for the other operating conditions, we see that all of them are below the value of 1. In a couple of cases, like the downward and the high lift operating conditions, they are very, very close to 1. So nominally, maybe we just managed to maintain the exact same performance as the baseline design, but the other 3 all managed to see improvements. And I should comment that there is no guarantee when you use a weighted sum of multiple objectives approach like this that you will see improvement in all of your objectives for your best design. It's entirely possible that based on the weighting that you assigned, this substantial improvement that we see in the cruise drag objective could more than compensate for a slight increase in drag, for example, in one of the other less significant operating conditions. we were very pleased to see in this case that the algorithm was actually able to identify a design that had better performance in all of these objectives simultaneously. Let's go to the next slide. So let's look and consider now the other two objectives, port and starboard pressure recovery. These you're trying to maximize, so values above 1 are what we're looking for. And, excuse me, you can see here that for all 5 operating conditions for both nacelles, the pressure recovery is in fact improved over the baseline values. Now take note that the scale of the y-axis is in fact quite small, so the improvement is minimal. We are very, very close to the baseline values. That is more than anything a result of the weighting that we assigned, given that drag had twice the importance of the pressure recovery and there were 2 pressure recovery objectives per design. It really means that the influence that these had on the overall performance that Sherpa saw for each design was pretty small. So certainly by going and changing the weighting, you might expect to see more improvement in these objectives. But the key thing to us was that we were able to find a design that managed to simultaneously improve all 15 objectives within that 80 total evaluations. And when looking at the kind of most critical objective, the cruise drag value, it was a 14% improvement, which is obviously very substantial. Let's go to the next slide. So let's take a second now and look at our constraints. We said that the distortion had to at least meet the values of the baseline design. Distortion is something that you want to be on the lower end rather than the higher end, so values below 1 or equal to 1 would satisfy the constraint. You can see here that for both the port and starboard nacelle, our best design had lower values than the baseline, and not by an insignificant amount. This is something that it's maybe kind of serendipitous. You don't really count on this because from a performance standpoint, any value less than or equal to 1 is exactly the same and wouldn't result in an improvement for the design. So Sherpa isn't by any means trying to reduce these values any lower. It happened to be that the best designs we found not only satisfied these constraints, they actually saw quite a significant drop compared to the baseline designs. The last thing I wanted to look at was lift. It's obviously a critical element of any aircraft design. It didn't show up in our optimization problem statement, but we do want to still track it and make sure that there's nothing too dramatic happening here. We considered including it, but decided given the total number of objectives that we had already, and that it wasn't the main focus that we're trying to do, that we would kind of leave it out and sort of see what happens. Always having the possibility later on to go and kind of extend the study, including lift as an objective. So you can see here that for our best design, we're within plus or minus 2.5% of the baseline lift across all of the different operating conditions. And for the purposes of this study, that was definitely within the margins that were acceptable to us. So a brief comment on what we would have done if, for example, we'd seen like a significant reduction in lift for maybe the cruise condition or something like that, is that we could actually take all of the designs that we'd already run and we could sort of resend them through Sherpa with the updated problem statement. And it would sort of reevaluate those designs within the context of this new problem statement and then sort of continue the study having learned from the designs we'd already run. And this is critical, especially when you're running, when each design represents such a significant investment as it does with this problem. You don't want to be left in a position where you ran 80 designs, you decide that you need to make some modification to your problem statement, and you sort of have to start all over from scratch. We'd be able to sort of retain and learn from all those designs kind of regardless of the changes that we made going forward. So let's, I think, move to the final slide. Oh, it's actually not the final slide. I think we have one. If we go to the next slide, yeah. One of the things that you want to do with design exploration is not only manage to find a good design, but also utilize all that data that across all the 80 designs and 5 operating conditions to increase your intuition, your understanding of the fundamental engineering, and what really kind of makes a good design. And an example of some of the tools that we might use to do this here is being shown. It's called a Baruta sensitivity calculation. It typically, so sensitivities are something that I think as engineers we're always interested in understanding the relationship between our input parameters and our responses and which ones are most significant. Classical sensitivity techniques, they just don't respond well at all to data that was generated by an optimization algorithm. There's a lot of bias clearly in the sampling of an optimization algorithm. That's on purpose. It's meant to kind of focus in on areas of the design space that it finds most interesting. And what that typically does is it just means any sensitivity calculations you might try and do, you really can't trust them. They're not going to be meaningful. The Baruta calculation takes advantages of some techniques that have been developed in data science and using machine learning. And it relies on a random forest generator to kind of interrogate the underlying designs and come up with a qualitative measure of sensitivity. And I'm not going to go into all the technical details. I think a lot of these data science techniques are new to most of us who are more traditional engineers and things like that, but they're starting to make their way into our tool set, because more and more, instead of looking at data from 2 to 5 designs, we might be looking at data from tens to hundreds of designs. And so we really need to start leveraging some of these techniques from the world of data science. Basically, what we're looking at here is a ranking of all the different parameters for our 3 objectives: drag, pressure recovery for both the port and starboard nacelles. This is just the data for the cruise condition. So we get another plot like this for each of the other operating conditions. What was kind of interesting to see is that each of the objectives was kind of dominated by the same parameter, which is the inlet diameter for the nacelle. And I want to sort of emphasize that this is qualitative. A positive value doesn't indicate a positive correlation. It doesn't mean that if you increase the inlet diameter, you're going to increase the objective. It's really just a magnitude and not a direction. It says that this parameter is determined to have the most significant impact on the overall results. And it's kind of interesting to see that if we look at the comparison between the port and the starboard nacelles, the sensitivities are not the same. Yes, they are both, the largest sensitivity is to the same parameter, but if the magnitude is quite different. And then if we look at the other two, the second most important parameters, they're very different. So I think there's a lot of great information here, but certainly it allows us, as we go forward and we design products like this in the future, we approach the design space with a better intuition about what is significant. Perhaps we want to expand the design space around that inlet diameter. Perhaps we want to even look at adding some more degrees of freedom to the nacelle inlet, because we recognize the potential that it has to improve the performance here. So let's go to the next slide. Just kind of in summary, the purpose of this project was really to take an application that has real-world engineering significance, that takes all the complexity that goes into evaluating the performance of something as sophisticated as a business jet, and to use a design exploration strategy on it, looking at the automation and seeing how much improvement we can get. I'm very pleased with the results. That for the 30 days of compute time, we managed to, get a 14% improvement in that principal objective, while simultaneously also seeing at least some improvement in the other objectives and satisfying all 10 constraints. So with that, I think, Jay, we'll pass it off to you to handle the rest of the call.